Thank you so much, Rami, and thank you all for attending. This is a treat to get to connect with the Petroleum Engineering Department. I feel like even though we share the same building, we don't often connect enough like this. So it's really an honor and a pleasure to get to do this today. So if you wanted to connect after my talk as well, feel free to just come by my office or send me an email. I'd love to talk with any of you if you find the research interesting or you wanted to ask more about it later. I also have the chat box open, so if you wanted to uh, put a question in the chat box during the talk, I will hopefully see it there as well. Okay, so let's get started. So the title of the talk is Keeping Pace for Fatigue. And fatigue is something that is interesting to me, and you'll see why in a little bit in the talk, but particularly I'll be talking about two metal systems that my research group studies on shape memory alloys and then 3D printed metals. Up front, I want to acknowledge the people who supported this work. So most all of the work is done by students like you. So Ethan is the student doing most of the shape memory alloy work, as well as being supported by Emma DeHarsh. And then on the 3D printed metal side, there's Kendall Yetter, Nathan Rendon, and Rianne Brown. So great team of students here, and I'm happy to get to work with them. Also, for the additive manufacturing, the 3D printed metals, we have a collaborator at Purdue University, and that's on our project that's with the Office of Naval Research. So I'll present later on our 3D printed metals work for this project. Some other funding that we have is through the Haythorne-Waite Foundation and the ASM SMST Society. Here's an outline for the talk. The first thing I'll do is just introduce why we care about metals and lasting long time for them, why we care about fatigue in general. The second part I'll share is understanding fatigue in the memory metal or shape memory alloys. And then the third part will be about our work on 3D printed metals and the surface treatment that we're doing for it. But first up, let's talk about why we care about fatigue in metals. So an example that I like to share is the wheels of the Curiosity rover. So in 2012, the Curiosity rover landed on the planet Mars, and NASA, within a little over a year, they started to notice some cracks on the wheels and these large punctures even in the aluminum wheels on Curiosity rover. So NASA is always doing new things. They're pushing the limits on what we can do as humanity. So anytime we do new alloys or new applications, we often encounter challenges with structural durability. So that's what NASA encountered here. And I'm a runner, and the analogy that I see in this is that a lot of times the way we push our metals to the limits in our structures and engineering systems is just how runners push themselves to their limits during a race. So engineers can design the pace for a metal structure, meaning how much stress it experiences and how often it experiences that stress. So what NASA did with the Curiosity rover is they make it drive shorter distances and at a slower pace. So its 2-year mission, originally, it's still going. It's now been on Mars for 9 years, and it's still collecting data, still doing work. It just doesn't drive nearly as far as it used to. So NASA changed the pace. This is also an example of runners who are known to be good pace keepers. So one example is Des Linden. She won the 2018 Boston Marathon really because she had exceptional pacing. Many other runners in this race went out way too fast because they didn't appreciate the weather conditions for the day. But Des Linden did. She paced accordingly, and she ended up winning. But there's a problem with this. So normally we can't change the pace of a component. Once it's in service, it's gone, and the engineers can't choose how fast to push the limits on it. So this is why we see things that fail. So I'll give a couple examples here of some things that have failed. So fatigue is a major problem even in well-established applications. And a couple examples would be this engine fan blade failure. This was almost exactly a year ago. This flight took off from Denver. It was headed to Honolulu, but it didn't make it much outside of Denver metro area before this fan blade broke. So this is a titanium fan blade. It has hollow features inside of it. And there was a fatigue crack that was beginning that went undetected during inspection. This is just one example, unfortunately a relatively common example. There's roughly 1 per year of these fan blade failures on passenger aircrafts. It's like a 1 in 10 million kind of event. But thankfully no one lost their life in this event. There's fatigue failures all over the place, though. It doesn't have to be kind of a high-profile event like this. For example, in cardiovascular devices like stents, you can see lots of fatigue failures. So this is a stent in a popliteal artery. So that's the back of your knee. Particularly people who struggle with diabetes or poor blood flow in their legs will get a stent in this location. But because your leg is bending at the knee, it tends to be a place where the stent cracks. So where the stent has cracked in these two spots shown by these arrows, there's not good blood flow there. So the stent is not operating like it should, like a stent. So fatigue failures like this cause a lot of problems. They cost a lot of money. They're responsible for about half of all mechanical failures or more, and they cost the country roughly 4% of our GDP. So it's almost $1 trillion if we're talking about like stimulus packages. These are like stimulus package level kinds of things that it's costing the country every year just in fatigue damage. And this problem of fatigue, it's not going away anytime soon because we're always developing new materials and new ways to use these materials. So new materials could include new alloys, like shape memory alloys. And by the way, NASA is going to use these for the next generation rover wheels. So for the Artemis mission, putting people on the moon again, the moon rovers will use these shape memory alloy wheels. Also, there's new ways we can make materials. So 3D printing is a big one. We can 3D print lots of different metals, such as this magnesium implant. So with these new materials and new manufacturing processes, we have new challenges from fatigue. So this means we need a better understanding and control of fatigue to keep up with the new materials and processes that are rapidly being developed. So this is where my research group at the University of Tulsa tries to carve out our little expertise in the world of fatigue. We're looking to discover mechanisms of damage in structural materials and pioneer pathways to improve their durability and performance. So this was our group photo last summer. Had lots of undergraduate researchers as well as our 3 graduate students in the group. And you can look up our group website here. We're amdg.science. That's for Advanced Materials Design Group. So we have 2 things that we do to work towards our mission. The first thing is we do a lot of groundbreaking experiments. So we're trying to uncover new damage mechanisms that haven't been able to be seen before. One of the key things that we do is we make strain maps. So this is a high magnification strain map around a crack tip, and it's in a nickel titanium shape memory alloy. I'll talk more about these data later. The second thing we do is new surface treatments. So the surface treatments we develop are particularly using a deposition technique called atomic layer deposition. And that'll be in the third part of my talk when I talk about our work with 3D printed metals. So just a high level overview of where we work, kind of the space that we work in. We do mechanics of materials and fatigue. We're strongly emphasized on metals in our group as well. We study corrosion a little bit, so like how metals rust. It's not just steel that rusts, it's aluminum and titanium and many other metals. We do surface science and also metallurgy, and then we're putting these together for that surface treatment that we're doing. And then our core capabilities, we do highly experimental work, not a lot of computational work, mostly experimental. We characterize a lot of materials, particularly with microscopy and diffraction. And then we do a little bit of thin film deposition. That's our coating technique that I'll share. And then as far as where this is relevant, so aerospace, automotive, defense, manufacturing, biomedical. And I think energy, you could throw an energy on top of all of these. As you know, as energy folks, energy is really prevalent in almost everything that we do. So it's there for metals work as well. So next up in my talk, I'll share about our fatigue studies recently in the memory metal of a shape memory alloy. And I'll have 4 parts to this talk about the section on the shape memory alloys. And I'll start by introducing what shape memory alloys are. So shape memory alloys are an interesting class of metals, and they have reversible solid-to-solid phase transformations. So just how water has a phase transformation between ice and liquid water and then gas or steam, there are solid-to-solid phase transformations in this material. It's the atoms reconfiguring their shape. So we can do this in 2 ways. We can have the shape memory effect where we thermally activate the phase transformation, or we can have a mechanically activated transformation for superelasticity. So the typical stress strain curve for a metal looks something like this, where there's an elastic region that we load, we induce plasticity, and then we unload and there's some residual strain left, like the plastic strain. But shape memory alloys, on the other hand, undergo this superelastic effect where we look like this region of elasticity runs out and we have what seems to be plasticity, but it's actually the atoms shifting their configuration. Instead of trading their location with their neighbor and inducing slip, they're actually just bending a little bit on their angles in the lattice. So this bending of their phase from austenite to martensite is reversible. So when you unload the stress, begin unloading the material, you go back to the cubic phase that you started with, that austenite. And this gives rise to a large recoverable strain, and it's the superelastic effect, we call it. So we use shape memory alloys for some niche applications. They're not used all over the place, but here are the main applications. So the big one is cardiovascular implants. So stents, heart valve cages, catheters, guide wires. These are often made of shape memory alloy, nickel titanium. And nickel titanium is the key alloy here. There's millions of these procedures every year for these cardiovascular implants. Also, they're used in root canal files. So if you've had a root canal file, root canal procedure, likely that was a shape memory alloy that was used for the drill. And then NASA uses shape memory alloys for certain applications. So this goes back many years. So for example, when the Hubble telescope was launched in 1990, its solar panels were deployed and kind of spread out like birds' wings using a shape memory alloy. NASA's continued to use them over the years. They developed these span-wise adaptive wings where the wingtips can be down for stability during a low altitude part of the flight, and then they can flip them up for fuel efficiency later in the flight. Those are solid state actuators with shape memory alloys. And also they use the superelastic effect for these tires. So these are going to be on the Artemis mission for our next lunar rovers. So the studies that my group has been doing, and this goes back to work that I began in graduate studies, we're looking at different knobs to study the response of these shape memory alloys. So a few of the knobs that we use are grain size, texture, and temperature. So when we change the grain size, we get very different stress strain responses in the material. Same with the texture, whether we have a rolling direction or transverse direction, parallel to the tensile axis of the material. And then also we can change the temperature and get very different mechanical responses. So we can change the temperature by, say, 35 degrees Celsius, and we go from this stress strain curve in blue, where we bottom out and we get a lot of plasticity, to a stress strain curve that has superelasticity, shown in the green one here. So it's really remarkable what we can change with temperature. And these are going to be the emphasis of the studies today that I'll share will be on the temperature as well, but I'll flash back to some of the prior work on grain size and texture. So there's one challenge when we work with shape memory alloys, is that they don't follow the theories that we would expect for metals. So some of these theories include something called the Schmid law, which relates the orientation of grains and their relationship to the direction of stress to when they're going to start to yield. Or for shape memory alloys, it's when they're going to start to transform. So shape memory alloys don't follow this law at all. Also, they don't follow linear elastic fracture mechanics. Now, this is true for different kinds of metals as well. Not all metals follow linear elastic fracture mechanics, but shape memory alloys do so in a weird way that's path dependent and also highly temperature dependent. So it makes it difficult to make fatigue predictions about shape memory alloys. So because of this, there's plenty of room to improve in how we design shape memory alloy devices. So leading up this charge are companies in the cardiovascular device industry. So they're motivated by failures like this and the stent that I showed earlier. Now, something to note in the stent is there won't be patient mortality necessarily from this stent. Even though the stent's not doing its job, there'll be a lower quality of life perhaps for this patient. They might need another stent put in, but there won't be mortality. However, there are cases when failures are not acceptable because it could lead to patient mortality. And these are particularly in the transcatheter aortic heart valves that have been released lately. Some of these are devices for adults, but there are also transcatheter aortic heart valves for as little as premature newborns now. So we really have to be careful about how we engineer these. The bad news is that we are way over engineering these devices in terms of how large they are and how invasive the procedure is for the patient. So if we could have a better handle on when failure would happen in these devices, we'd have much lower and much less invasive procedures. So that's a lot of what motivates shape memory alloy research. So the key question is, how do our process-driven properties drive performance? So if you're familiar with material science analogies, going from the process to the properties to the performance of a material, these are the relationships we look at. So the processing, we have various processing changes we can do to shape memory alloys. And then we ask, how does this influence the properties that we see and ultimately the performance that we want for our devices? So the two things that I'll be cluing in on today are the transformation temperature and stress, and then the defects and inclusions and their role on fatigue. Okay, so next up, I'll share the methods that we use on studying these materials. So first off, it's important to know that there's two different kinds of fatigue for shape memory alloys. There's structural fatigue, and this is what we think of when we typically say the word fatigue. We mean cracking in the material. There's another kind of fatigue, though, with shape memory alloys, and we call it functional fatigue. So this means less transformation and more plasticity. So if we cycle the material just tensile loading and unloading, so this is one load in gray, and then we do it 25 times and we get to the purple line. This is after 25 cycles, we have less transformation strain that's recoverable. The strain axis has shortened up, and also we have this residual plasticity left. This is functional fatigue. The material has not begun to crack at all, but we're still seeing damage forming in the material. So we use two different kinds of experiments to study these two different kinds of fatigue. The first thing we do is compact tension samples for structural fatigue. And then the second kind of sample is just a normal dog bone, like uniaxial tensile samples. And we load them and unload them a number of cycles, it could be thousands of cycles. And that's how we get our fatigue damage to form. And then we look at the samples as the damage forms over time. So we're making these observations with cameras and also with microscopes, and we can span then from the millimeter scale to the micron scale. So for example, on the millimeter scale, we can look at crack growth rates, and then on the micron scale, we can look at the crack tips as they open and view the crack tip opening displacement directly. So the technique we're using for both length scales is something called digital image correlation, or DIC. DIC is a cool technique because it measures local deformation. So normally we measure deformation with strain gauges, but strain gauges just give us one number for the whole sample. But with digital image correlation, we can get lots of numbers across the sample and get local measurements of strain. So this is a stress strain curve that I'm going to show for shape memory alloy nickel titanium. And you can see why the local information from digital image correlation is valuable. We can see where the phase transformation starts and right when the atoms start to get shifted into their martensitic phase. And then as the material unloads, we can see where the phase transformation is reversed. So I could watch this video over and over again. There's so much to see. There's these fingers of the transformation propagating and nucleating. And then there's even this kink in the sample macroscopically as the atoms shift, the whole sample itself shifts over. So it's just a beautiful phenomenon, I think. And we measure this with digital image correlation. So the way it works is we track subsets in what's called a speckle pattern. So you notice that these samples here have dots on them. So it's black and white dots that we're tracking. And we call that the speckle pattern. So you get an initial reference configuration of the sample. Then we watch it deform over time, and we can get displacements from where the original positions were in the pattern to their current positions. And we get this displacement map then over the surface of the sample. We can take the spatial derivative of the displacements and get the strain map. So this is the core of digital image correlation. And then the cool thing is we can get the images from really any length scale. So often we'll use cameras on the millimeter length scale. So these are similar to the cameras that you would find like in your phone or a DSLR camera or a mirrorless camera, similar cameras to that. We look at our sample and we have a pattern of paint that we're tracking over time. But we can also pull the sample into the scanning electron microscope and look at the pattern formed by nanoparticles. So we can get a pattern of nanoparticles such that we can track where they go and get strain in our sample. So I've done some work in the past to optimize these measurements, and this ended up being important for tracking the crack tip in shape memory alloys. So some of the optimizations are shown here. Doing cross polarization, you can get better correlation, and also doing an optimized speckle pattern, you can get less noise. So both of these together means we can pinpoint exactly where the crack tip is in a shape memory alloy sample while it's cracking. I'll show a video of this. So this is one image every 1,000 cycles during loading, and we can watch the crack grow. So I'll show the video again. The crack starts up top, but then there's a second crack that forms underneath, and that second crack ended up being the crack that mattered and grew the longest. So we can find the crack within about 25 microns. Here's just a summary of what I showed. So over a couple thousand cycles, we had a new position for the crack tip. So this was interesting because a global technique like measuring the crack mouth opening displacement with like an opening gauge, it wouldn't have known that there were two different cracks here. It would have just thought that the sample was cracking with just one crack. So this is the power of these local measurements. I've also worked to improve the measurements in the scanning electron microscope. So you can use, instead of using the built-in microscope scan controller, you can use an external scan controller to drive the coils on the microscope, and you end up getting a lot better digital image correlation data. So some work that I've done in shape memory alloys advanced that. So once we get into the scanning electron microscope, we can measure crack tip opening displacements within 20 nanometers. So that's about 200 atoms length. We can see the crack open up just by that small amount, and we can quantitatively measure its crack tip opening displacement. This is interesting because normally the crack tip opening displacement is something we estimate based on models from elasticity theory, like linear elastic fracture mechanics. But again, this alloy violates linear elastic fracture mechanics, so we can't do that. So we can zoom in on the crack tip and see the crack tip itself. So a result that we had on prior results is that we can see the smaller crack tip opening displacement on the micron scale from our scanning electron microscope corresponds to slower crack growth rate. So these are different grain sizes of the shape memory alloy. And although the fatigue performance in functional fatigue is not great for the largest grain size, we find that it has the best crack growth resistance. And this was due to the roughness-induced crack closure that it had. But it was interesting that we captured the trend that we saw on the macro scale in our crack growth rate versus stress intensity. And this intermediate grain size had the faster crack growth rates. And then they also had the largest crack tip opening displacements. So this work was picked up by the cardiovascular device community, and I've been seeing some alloy development come from them. So interestingly, they're starting to develop alloys now with 10 and 20 nanometer grain size for use in cardiovascular implants. But it was from this earlier work that we did on the grain size study. Okay, so the next thing though that I want to share is our work that we've been doing more recently with temperature. So temperature is that big knob, and it really dramatically changes the mechanical response of nickel titanium shape memory alloy. So recall, if we just go up from room temperature by 35 degrees on an alloy, we can get the superelastic effect, dramatically different mechanical response. And then if we keep heating, we can eventually get to a temperature where we no longer induce the phase transformation, and the material behaves more like a typical metal. So the reason for this, again, is from the solid to solid phase transformations, but I wanted to show this plot. It's the heat flow with respect to temperature. So we call this differential scanning calorimetry. And the thing that I wanted to highlight is it's path dependent. So we can begin at room temperature in the martensite phase, heat up into the austenite phase, and then when we cool off, we go into something called the R phase. It's actually a different kind of martensite that's distinct from the original martensite. And it's not until we cool below about minus 50 degrees C, at least for this alloy, to get the martensite finish. So the path dependence here ends up being something that's important when we study the temperature effects of the material. So we can get the mechanical response to change dramatically just with minor temperature shifts. So these are the changes from room temperature up to 57 degrees. And then if we keep going, we keep changing the mechanical response. But the knowledge gap is there's no work to date that has measured this cracking with more than 5 temperature points. And then the thermal hysteresis that I mentioned, like we start in martensite phase and go to the R phase, that's been completely overlooked in the literature. So what we've been doing at Tulsa is we developed a custom thermomechanical fatigue system. So we can heat our samples to 150 degrees C and cool back to room temperature in 20 seconds per cycle. So this is a rapid thermomechanical fatigue system. It was actually a capstone design project for some of our seniors last year in mechanical engineering. One of the keys is we use very small samples. They have a small thermal mass. They're only about as big as your small finger, and they're very thin. They're like 0.5 millimeter thick. And this lets us heat them up and cool them off really quickly. We used some process air heaters and chillers like you would find on a factory floor. And we use our digital image correlation cameras. So this is a cool custom setup that's really letting us do some groundbreaking work at Tulsa. So I'll show some of the results from this. So if we apply a constant force, this is a sample that we have just a dead load hanging on. So it's opening the crack a certain amount under this dead load, but the crack is going to open and close based on the different phases. So we're watching the crack tip opening displacement with respect to temperature, and we're beginning at room temperature. We're going to heat it up and then cool it off into the R phase. So initially what happens is the crack rapidly closes, just like a zipper, just closing up the crack. And then it's in a mixture of austenite and martensite, but if we keep heating, not much really happens. So it stays closed and we just get, this is actually a thermal expansion effect beyond this, okay? And then if we cool off, the crack opens back up partially, but not all the way. So this is that hysteresis that has been overlooked in studies on the cracking of shape memory alloys. And it's pretty interesting to me, just the fact that this material, as you heat it up, the crack will actually close. It pulls up the weight, it pulls up the dead weight that's hanging on the sample, and it closes the crack. So it's pretty remarkable what this material will do. So if we do a bunch of these tests with different dead weight amounts, so this is increasing dead weight, it's the color starting at nothing, increasing the dead weight to a maximum amount, and then going back to nothing, we get this consistent hysteresis where the crack tip is higher in the beginning and then it closes, but it doesn't go back to where it used to be. We can also look at these data in terms of plotting the crack tip opening displacement. And sorry, this is a typo. It should say CTOD here instead of delta V, but it's a crack tip opening displacement with respect to the applied stress intensity for the various temperatures. And what we can see is there's this non-monotonic effect, whereas we go up to the phase transformation temperature, we get the most opening. And then on the other side of the phase transformation temperature, we get a little bit less opening. And also it's path dependent. So these are all on the heating side, but if we look at the cooling side, that hysteresis reverses and it goes in order of the approaching temperature. So this is where we're at on this study. We're trying to understand this interesting hysteresis and why this is, why the crack opens more as you're approaching the phase transformation temperature on heating, but then it opens less whenever you're approaching it on cooling. So one of the things that we're improving upon is we're getting some new samples. So these samples here, they kind of bottomed out before we reached the martensite finish temperature. And the cooling on our system is not as good as our heating. We have a really good heater, but the chiller, it's kind of difficult to cool things on it. So what we're going to do is we have a new ingot of alloy that we've been working with a company from Italy called Sace Getters on. We've made these samples with a laser cutter and we've polished them. And these samples will shift our whole response up by about 75 degrees C. So we'll be in the sweet spot of our custom thermomechanical tester then. So I'm really excited to get these experiments going. And actually, I was just down in the lab before this talk, and Ethan, one of the graduate students, is working on setting up these new samples. We have them, and he's getting it running. So really excited about this work, but this is where we left off. Okay. So the next thing I wanted to share, the last bit about our shape memory alloys, is about inclusions. So the inclusions that we see on the sample are important, and I'll share why. So if we look at where failures occur in these cardiovascular devices, many of the failures are due to defects on the surface called inclusions. So these inclusions look something like this. You can view them in the microscope. This is 10 microns, so the inclusion is about the width of your hair. If you look at one hair, that's about how wide the inclusion is. You know, the hair would be the whole height of this image. The reason these inclusions cause failure is because the device width is very small and you get a stress concentration from these inclusions. But we're not sure exactly what about the inclusions, whether it's these voids around them or the particular shape that causes the failure. But we do know they cause the failure. So there was a recent work in 2020 that showed that the vast majority of failures in shape memory alloy devices had an inclusion at the crack site. And this was from 354 samples that were failed in fatigue. So this is what one of those inclusions might look like. And this is like a bird's eye view, and this would be the fracture surface. So like the crack, we're looking down on the inclusion here, and then the crack started here and propagated that way into the sample. So what our group has been looking at on these inclusions is we'll pull them into the microscope, do some fatigue loading, or pull them out of the microscope, do some fatigue loading, then go look at them again, go back and forth between fatigue loading and then back to the microscope. And we see where is the crack starting? Where do we see the crack form first? And the interesting thing we found is that there's big inclusions. There's one that are about 50 microns long, like these, we call them stringers. They don't have cracks that are growing, so they look pretty much the same as we apply more fatigue cycles. However, where we do see the cracks form are these very small these very small teardrop inclusions. So these teardrop inclusions are about 10% of the size of these large ones, but they're the ones that are starting the cracks. So we've been scratching our heads as why this is happening, but we have two hypotheses that I'll share with you. And this is still active research. But the two hypotheses are, first, the cracks could be driven by tensile residual stresses that formed when these inclusions did not break up during the cooling and drawing process. So during the mechanical forming of the material, it involves heating up of the material. It's a hot drawing process to make tubes of nitinol, and from the tubes we get devices like the stents. But the problem is these teardrops, they will have a different thermal expansion coefficient than the metal, because these little inclusions in the material are not metal. They're actually an intermetallic, so something like a carbide or an oxide ceramic. So these ceramic inclusions will not expand as much or shrink as much whenever they cool, but the metal will. So you can kind of see this in the shape. It looks like the metal wanted to squeeze in on the ceramic. And same here, it's kind of like the ceramic is pushing the metal out. So we suspect that this could be leading to tensile residual stresses in the material that are causing the cracks to start here in these teardrops first, instead of over here in these large stringer inclusions. So this was a really exciting finding. We had it maybe a month ago, and we've still been trying to figure out why it's happening. But we're excited to share this with the wider community as well. The other hypothesis we have is that there could be subsurface effects involved. So if we cut into the material with a microscopic mill, it's called a focused ion beam mill, and we do serial sectioning, meaning like we slice more pieces of the material away and look at the material as we do cuts into it, we see that there are holes underneath these teardrop inclusions. You can maybe kind of see them there. So it's kind of like a tip of the iceberg effect. It's like we're looking at this small inclusion on the surface, but there's these holes and this other larger shape underneath the surface. So this is maybe one of the reasons why we think the failures could be starting at the teardrop inclusions instead of the stringers. But we're still doing a lot of work to figure this out, and we want to get to the bottom of this. I'll say another thing that we've been doing recently. I don't have a slide for this, but we've been identifying the composition of these inclusions, whether they're oxygen rich, meaning they're an oxide, or if they're carbon rich, meaning they're a carbide. So we've been able to identify what their composition is using electrodispersive spectroscopy. So it's kind of a new development on it. But anyways, we're still trying to figure it out. Okay, so that's kind of a bird's eye view of what we're doing with shape memory alloys. So I'm going to shift gears to the surface treatment that we're doing on 3D printed metals. So 3D printed metals are awesome. It lets us do designs for structures that we could never really do well with conventional machining or forming techniques for metals. So one of the things we can make are these microlattices. So microlattices are a way to get high specific strength and specific stiffness out of metal by making a lot of air pockets within the metal. So 3D printing is really good at this. We can make some of these microlattice structures pretty well. The problem is there's poor fatigue performance. So we've increased the surface area to volume ratio a lot. And because of that, and I'll show another result, I'm getting a little bit ahead of ourselves. Because of that, we get very poor fatigue performance. So if we make a microlattice material, and this is from my colleague at Purdue, Mike Sanjid, this really inspired our project with the Navy. If we look at the fatigue life, this is the stress amplitude of fatigue versus its life in number of cycles. A conventional alloy would have a fatigue life of this red curve. If we go to a 3D printed solid material, we get about half the fatigue performance. Right away, we're cutting off about half of our fatigue life. But if we go into a microtruss, we get about 3 times less than the solid 3D printed part, the solid additively manufactured part. So it's a factor of 12 difference between the 3D printed microtruss and then the conventionally manufactured material. So the goal of our group broadly in this work is to bring the black curve up to where the blue curve is, to where we can reduce these effects of the surface to area to volume ratio that has been introduced. So as I implied, it's surface roughness that is the primary driver of fatigue performance for many additively manufactured metals. So if we look through the literature, like this was a review paper that studied many different studies of fatigue performance in 3D printed metals. What they found is that surface roughness is the key driver for 3D printed metals and their fatigue performance, even in the presence of relatively large internal defects in various microstructures. So surface roughness is key. This isn't really surprising when you look at the surface treatments, when you look at the surface roughness on 3D printed metals, they're very, very rough. So we look at these powder particles and how they form during the layer by layer scanning of building up the material. And we get these defects like this. They're very sharp on the edges, and it's from each layer of powder forming up. So these are so rough, in fact, that I have been skimming through this textbook. This is a classic textbook on how to deal with metal fatigue and defects on the surface. And the surfaces that we see in 3D printed metals are so rough that it's off the charts for our theories that we had back in the 70s and 80s for how to treat surface roughness on metal. It's just remarkably rough, and our theories don't even deal with it yet. So it's a big problem for the 3D printed metals community. So what we're proposing is a new class of surface treatment. So if you look at the existing surface treatments that are out there, they have two weaknesses. Either they cannot reach within a microlattice or within that complex geometry that I showed, where we have lots of air pockets. So they might be like a line of sight technique, like shot blasting or machining and grinding. These are all line of sight. You need to be able to see and reach to the part that you're going to treat. Or either they don't reach within the microlattice, or they don't have uniform material removal. Meaning if it's going to remove some material over here, then on this part over here, it will remove the same amount of material. So the liquid techniques do reach within the microlattice. These are liquid-based techniques of acid etching or electropolishing, but unfortunately they don't uniformly remove the material or smoothen the material. So here's an example. This was a paper from last year, and this group used a liquid-based technique, but it had non-uniform removal of the material. So they did electropolishing. They even optimized the cathode shape to go into this specific shape of their microlattice. But unfortunately, what they saw was there was still non-uniform material removal. So before they started out as the same size, and after they got some that were quite a bit smaller than the others. So this was non-uniform material removal. And what this does in fatigue is it makes weak links. You know, fatigue is going to fail at the weakest link first, and it would be at this weak link then. So we can't have this non-uniform material removal. So what our group is working on is a new technique that uniformly smooths structures like microlattices that are complex. The way that we're doing this is a gas phase based technique. So we're doing a coating that is applied in the gas phase. So it's a coating technique that I'll share in just a moment. It makes a very uniform conformal coating all over the part, even inside the microlattice. And then we activate the selective melting of the surface during heat treatment. So the heat treatment, we can melt just the surface. And the way we do this is with something called a eutectic reaction. So we're very familiar with eutectic reactions, even if it sounds like a fancy word. You know of a eutectic reaction. So on our roads, outside, on campus, or whenever we have these snowstorms, we put salt on the roads. So chloride, the chlorine in the salt, the chloride ions, forms a eutectic reaction with water. So the water has a lower melting point, or the ice actually has a lower melting point in the presence of chloride ions. So it's a lower freezing point of the water in the presence of the chloride ions. And this phenomenon is seen all over the place. So if we look at particular metal alloys that do this eutectic reaction, we can do it with aluminum and tin, drop the melting point here. We can do it with titanium and copper, same thing, and zinc and nickel. So these are commonly 3D printed metals, and we have a eutectic formula for all of them. So for water, it's something like, I think water alone, freezes at 0 degrees Celsius. And then when you add chloride ions, this is around minus 26 degrees Celsius. So that's what gives us the good melting on our roads whenever we salt them. So what we're going to do, or what we are doing, is we're doing these conformal coatings with something called atomic layer deposition, or ALD. ALD is a technique that's used in Silicon Valley, and it coats these nanoscale features. So very small features, ALD can coat all the way down into these microscopic features and all the way back up. And notice how uniform this film is. So this is an ALD film that's almost exactly the same thickness all the way up and down this trench silicon sample. So this is the classic technique used in Silicon Valley when we need to coat something very uniformly and very precisely. So it builds up the layer of the coating, literally one layer of atoms at a time. And it's the most precise coating technique that we have available. The cool thing is it's also fast. So normally it's slow, like in the lab, we get about 1 angstrom per minute. That's one layer of atoms per minute in our lab. But in industry, it can be scaled up to faster than a nanometer per second, particularly if you use a roll-to-roll processing technique. So as I mentioned, we're doing these eutectic reactions to activate surface remelting. So we're targeting the titanium copper system to start. So our copper coatings will activate surface remelting during a standard titanium heat treatment. So it's common to do a heat treatment of your titanium part 900 degrees C for 2 hours. That's just the textbook titanium heat treatment. The good news is that will activate a liquid eutectic. If we look at the phase diagram of pure titanium versus copper, there's a liquid eutectic at about 25% copper, 880 degrees C. So these coatings on the surface are going to make just the surface melt, while the rest of the titanium will not be molten because it's up here at its melting point of 1670 degrees Celsius. So we've looked at various processes for doing this coating. We're zooming in on copper acetylacetate and hydroquinone. So we're reducing the copper ACAC with the hydroquinone to leave behind just the copper atoms. This technique was developed last year by a group from Finland, and we've been trying to adopt it in our ALD reactor here at Tulsa. But we're doing coatings on our parts and seeing how well these coatings form. We're also doing some interesting shapes of our parts. So we've boiled down a typical microlattice sample into just what we call a single unit cell. So this is an octet unit cell, 8 legs on it. We've done some finite element analysis to optimize the shape of it to get uniform stress throughout the base here of the part. Then we're also doing some dog bones. These are really, really small dog bones though. The gauge section has a 0.5 millimeter diameter, so much smaller than the typical dog bone. I think I have a dog bone over here. Hold on, let me show you. This is the size of a dog bone normally when we work with dog bones. You know, it's pretty big, more like the size of your arm versus like the size of a pencil lead. But this pencil lead size sample is what we're working with actually. They're very, very small. So we're going to do 2 heat treatments, and I won't bore you with too many details here. We'll do a standard heat treatment, but also a newer one called a super beta transist heat treatment. So this was developed a few years ago, and we're going to try it here in our furnaces at Tulsa. This could actually activate more of the surface remelting, so it could be favorable for our work. I'm going to skip ahead just a little bit. So we'll do some characterization before and after doing our heat treatment. So this project, we're 6 months into this 3-year project, so we're still kind of getting off the ground. But what we're going to do is we'll characterize the surface roughness with microscopy, also the microstructure with diffraction, and then we're going to measure the residual stress in the parts using synchrotron diffraction. So this is where our collaborators at Purdue come in. They're really good at the X-ray diffraction techniques in the synchrotron. So where we're at is we have these samples. They were just built earlier this month by a company out in State College, PA. So these samples, it's kind of hard to appreciate just how small they are. They're very, very small little samples, 0.5 millimeter diameter gauge section, and we have 500 of them that are little baby samples. So we put them into our fatigue testers, and we're doing fatigue testing on them both with and without the surface treatment. So we have these little electrodynamic frames and also a servohydraulic frame. So the key questions that we're targeting in this work is how much copper do we need to get an appreciable amount of surface smoothing? So we're applying the copper with atomic layer deposition, but we can also apply copper with electroplating. So this is an electroplated sample of aluminum actually, and this is a steel ruler. We're going to electroplate copper onto anything that conducts electricity. So the titanium will work just fine. The second question we're trying to answer is, does the surface remelting relieve beneficial compressive surface residual stress? So to improve the fatigue performance, we don't want to relieve compressive surface stresses because those are good. Those push the cracks closed. So that's one concern here, is that we might actually melt the surface but create a poor state of residual stress. This is where our synchrotron work comes in. And then finally, we want to find what are the process structure property relationships for this new process. So this has never been done before. We're kind of going out on our own by pursuing this project, but we hope it leads to a lot of really a new field and a new direction entirely. But we don't know where it's going to go. So we're using some theory like crystal plasticity and some modeling to predict these process structure property relationships. Okay, and this is the final slide for my talk. So I would love to take any questions that you have.
Thank you, Will. Very fascinating. So questions from the audience, please raise your hand. Wen.
Hello, Professor. Thank you for your nice presentation. My question is about your digital image for the super elastic alloy. Would you please, move the slides back to? I think one thing I didn't get it is about the cross-like strain. Yes. If you can play it, yeah. There's something, right? There's something cross-like strain. Why is so regular like that?
I'll even try to pause the video here. Let me see if I can pause it. Like here?
Yeah, yes, yes. Thank you.
Yes. So these are bands of martensite that nucleate and then they propagate, meaning they grow. But when they nucleate, they kind of come across as these little fingers. But it's you can solve using the theory of elasticity. You can solve for the compatibility of these two phases, the austenite and the martensite, and you get a favorable orientation for how their atomic planes line up. And this is what ends up being the angle that you see of these fingers starting. It's about 57 degrees for these angles, and that's what we see whenever we start the phase transformation locally. And then you notice that it's kind of like the transformation is the first in and then last out. When it unloads, you get kind of the reverse fingering as well. But good observation. Yeah, it's fascinating how this material behaves.
So a following question. So do you think, all the elastic material has this feature? This finger things feature?
Do we know how it has
yeah.
it?
I mean, so like the different material should have different angle, right?
Oh, yeah, yeah.
Okay.
Yeah, and
Okay, thank
broadly,
you.
you can see this behavior. It's sometimes called a Luder's band, and I'll put it in the chat box for how you spell Luder's. It's got that umlaut, so it's a Luder's band in steels. You can sometimes see this in other metals, but the key is it's not reversible in those metals. We're seeing it form and then disappear in the shape memory alloy, and steel is not going to do that unless you heat it up a bunch.
I see.
Yeah.
Okay, thank you.
Yeah, good question. Good observation.
Vinicius. Vinicius, we can't hear you. Make sure you unmute. Maybe while Vinicius works on the mic or types a question in the chat, just a follow up to Wen's question. So I think in linear elastic materials, I think is this sort of phenomenon something you would expect to see there?
Yeah, not within the linear elastic regime, at least. We have to, in steel, you have to begin plasticity to see the Luder's band, or even in the shape memory alloys, you have to go beyond the apparent elastic limit. It's no longer linear, and then we induce the phase transformation. So yeah, it's not something we see when we're just stretching the atomic bonds. Yep. Okay, I see the question in the chat box. More details on the image processing for this distributed strain measurement. Camera specs, frame rate, calibration. Yeah, good question. Maybe this slide could be helpful to see. So there's lots of different ways you can set this up. It's actually, I would say the key factor is actually the lenses. So the lenses tell you a lot, or you're going to pick your lenses based on the kind of measurement that you want to make. You can do it in stereo, and you can get all three displacements, or you can do it in just one camera, just not stereo, like monovision, and you get two displacements up and down, but you assume the sample doesn't move away from you or towards you, because if it moves towards you, it's going to appear like there was a biaxial strain when there really wasn't. So we make a plane strain assumption with the sample then. So yeah, you start with the lenses to choose the setup, and then the cameras, they're black and white. We don't care about the color. They generally have a high quantum efficiency, not necessarily any like a high resolution though. The highest resolution we use is maybe 12 megapixels. Frame rate generally slow, but sometimes people will do very fast DIC. So like with ballistic materials and ballistic experiments, you can still use digital image correlation. And then the calibration, that's a good question. So basically, if you're doing just monovision, one camera, you just need to calibrate the length scale. So that's just a reference to how wide your image is in physical space. If you're doing two cameras, though, you need to calibrate the positions of the cameras relative to their imaging planes. So you use a calibration grid to do this, and it's 3 points on the grid. And I'm going to pull up a website. I'm going to put a link in the chat that will help you if you're curious to read more about this. So hold on. There's a website in the chat that you can read. So this is a website I published a while ago, and I haven't really updated it much, but it goes through these basics of digital image correlation.
Thank you very much.
Yeah, good question. You got your mic working too. Good job.
Okay, yes. So, okay, I understand now the calibration you only need to have like a length scale. So you have a very good amplification on the lenses as well. Is that correct?
Sometimes, yeah, not always, but sometimes they are high magnification lenses. Yeah.
Just as an idea, do you think I could obtain something like that for like higher? So instead of looking so much into details, it's getting like kind of at a larger objects.
Absolutely. Yeah,
Okay.
absolutely. So people use digital image correlation on wind turbine blades, on bridges. I've even seen a study where people did digital image correlation on Mount St. Helens, like the volcano eruption. So you can use very large things. That's one of the beauties of the technique is it's the algorithm, which is based on optical flow for the mathematical theory, but the algorithm is independent of length scale. It operates in the pixel space, not with any physical length scale.
Okay, thank you very much. And usually how much time does the algorithm take to process these images?
Not bad, not bad. Like seconds per image.
Okay, that's fairly well. Okay, thank you very much. It was a really nice presentation. Thank you.
Cool. Thank you.
More questions? Maybe while more participants think of questions, I've got one for you. What does dynamic failure look like with super elastic materials?
That's a really good question. So it really starts to behave more like a typical metal. So the maybe I can pull up the temperature plot. So there's the range that's near the transformation temperature, which, by the way, the transformation temperature for this alloy that I showed here was 54 degrees C. But whenever you go into dynamic rates, it starts to basically go into this adiabatic state to where the events happen so fast that there's not enough time for the heat transfer to really take place. So it behaves more like a typical metal.
That's very interesting. So there's a characteristic time scale, and given strain rates beyond that,
Right.
I noticed, several plots. You look at stress intensity factors at the tip, and you look at the critical stress. How is the critical stress intensity factor, measured or defined?
Yeah.
Max.
That's a great question. Yeah. So this is a little bit of an abuse of the theory here. So we use the crack length. The crack length is proportional to the stress intensity factor. It's also proportional to the applied load. But then we just say the K over K max is a fraction of the load. So we didn't actually compute the K here. The reason being, we know it's violating linear elastic fracture mechanics. And that would be the way to compute the K, is with linear elastic fracture mechanics. However,
Yeah.
let me pull up a backup slide. Let me pull up a backup slide. So something we can do is the J integral. So instead of using the linear elastic fraction mechanics, we can do the J integral or the I integral. The I integral is the history dependent one. And we can do that with our digital image correlation displacements. So the theory begins to basically, we need to use the I integral anywhere where we have the transformation induced, and it's history dependent. But I didn't show the J integral here because it's basically we're not quite done with getting these calculations. But we can at least with confidence we can say that there's some sort of proportionality with the force. So that's the K over K max business.
Yeah. Yeah, we use a J integral approach on the computational side, with fracture propagation.
Cool.
But then that leads me to my next question. Have people studied fluid-driven crack propagation in these materials at all?
Not that I'm aware of, no.
Yeah, because that would add, a third sort of dynamic. And of course, you've got viscosity dominated and toughness dominated regimes. But then how that translates to this setting, that seems very interesting, fascinating.
Yeah, it's a fun space to work in. Like when we know it's not linear elastic fraction mechanics, and then we see what we can do, and then we're trying to get these results going with the data. Yeah, so we have a code that will compute the J integral from the DIC displacements, and others have done this before as well. But for now, we're just using that proportion, the K over K max. I can tell you study fracture a lot, Rami.
Yeah. More questions. We've got time for one more question, maybe. And if not, Will kindly shared his offered to speak with folks who are interested offline. So please join me in giving Will a virtual hand of applause. And thank you once again, Will. An excellent presentation.
Thank you so much, Rami, and everybody for hosting me. And again, I hope to see you all around campus. So don't be a stranger. Come on by and say hello.
Thanks again.
Thank you. Have a good weekend.
You too. Will, do you have a couple of minutes to hang back and talk once people sign off?
Sure. Yeah.
Yeah, this is very, very interesting. I work on sort of the computational side, and we look at primarily fluid-driven fracture in brittle materials and rock. And one. I looked at, looking at your setup, is there any potential to do somehow DIC with fluid-driven fracture?
Yeah. So the tricky thing would be you could account for the refraction that happens to the light as it goes into the fluid. But it's possible.
But even just forgetting the fluid, if you have this thin sample, you need to kind of contain, you need to adhere, I don't know, in 3D sort of, but one dimension is very thin,
Okay.
How to do that, to contain the fluid that's driving the fracture, while at the same time not altering, like seeing at the tip,
Right. Okay. So the cameras could view a dry location on the sample and
Yeah.
the other side
Hmm.
of the fluid. Yeah. Yeah.
The reason I ask that is right now, there's this big uh, challenge, with fluid-driven fracture under viscosity-dominated conditions. You basically see the crack tip move faster than the invading fluid.
Mhm. Okay.
And it's a thing apparently, but it's a theoretical thing, and I want to see it in a physical experiment. It would
This is
be,
sounds quite dynamic as well.
well, quasi-static, yeah, dynamic. I think uh, propagation. It's essentially, like this cohesive zone model. If you're
Mhm.
uh, you know but sort of seeing that in the context where there's a fluid lag
Mm.
between the fracture tip and the injected fluid. I don't know the time scales, frankly. Of
Hmm.
course it's material dependent, etc. But this is an unanswered question. In other words, Irwin's criterion, LEFM, what we get from that is, the energy, even energy approaches, what we get from that is, a criterion. Let's say, for instance, stress intensity factor being greater than, toughness, or greater than a critical intensity factor. But what it doesn't give us is a time dependent criterion. In other words, what is the velocity of the tip? It gives us whether a tip is currently in a stable propagation or not.
Right.
And I'm curious about, how one would go about combining experiment with some theory. We differentiated basically this constraint in time, and what we're missing is a closure law pertaining to the velocity of propagation at the tip.
The fluid. Yeah. Okay. This is interesting because it raises, it's something that I think would be relevant as well um, beyond like rock fracture. So I'm
No,
thinking
no,
of
yeah, this is
there's a phenomenon.
fracture
There's a
mechanics,
phenomenon
brittle
in,
material,
yes, there's a
but
phenomenon in solid state electrolytes for batteries that as
yeah,
you begin to fail the electrolyte, it begins in what's called a filament or a dendrite, say of lithium, that penetrates into the solid electrolyte. But the lithium behaves very much like a viscoplastic metal. It has a
mm,
lot of viscosity really, and it
mhm,
has Joule heating as well. It's getting hot, so there's lots of creep. But I could see this phenomenon as well, where the crack would move faster than the pressure from the lithium could apply, and the lithium could actually fill into the crack,
yeah,
but not as fast as the crack moves.
yeah. I
Hmm.
was just, actually, had a meeting earlier today with a collaborator on this, and it's a really important question, but I had the chance to visit Aris Rozakis's lab at
Yeah.
Caltech. He does interesting work, and it's really an open question, and the challenge experimentally is to somehow design specimens where you can see the strain field, the deformation, but then also have not affect, contain the fluid in the crack.
Hmm. Hmm.
So I was just curious to see, if you have this could be, a good way to collaborate if you're interested.
Yeah.
Yeah.
Um, the first geometry I think of is what you would use in a wedge test. So you could get two transparent beams like glass, and then this I've done a wedge test sample in the context of an adhesive. I can send you
Hmm.
the link to the paper. Um, but what you can see is the crack moving between the glass slides.
Oh, awesome.
So here's the
But then,
link.
but then it's moving into it's propagating a material sandwiched essentially by two layers. Is that right?
Yes, yes. So, the adhesive is involved there instead of
Mm,
just a monolithic
continuum.
material.
Yeah, yeah.
Uh, but you could still inject, instead of putting a wedge in
Hmm.
between the two beams, you could have a fluid take the place of the wedge.
Ah, I see. Yeah, yeah, that's exactly right. Yeah.
So we did this with, we did PMMA for the wedge
Yeah.
testing, and
Mm,
then you could see the crack move over time.
amazing. Awesome. Do we
Yeah, we
have capability at TU at the moment, or
um, not specifically, but it's not that hard actually to set up a wedge test. You can build a little wedge tester for under $1,000 easily,
no?
and
I
it's
mean,
just
the optics.
yeah, for sure, for sure. So we don't even need digital image correlation for it. So it's just a time lapse camera, basically.
Okay.
That's
Okay.
all we use.
And if we were to try, a DIC approach, I know at OSU, my collaborators, recently bought these $500,000 cameras,
Yeah.
very high frame rate. Uh,
Okay.
um, but I don't even know. I guess it would depend on the frame rates that we need. Uh, because
Right.
ideally we would want to compute or process the strain field as the crack is propagating, and
Hmm.
then on the fluid side we would look at rates and pressures, and that's easy to do, or I imagine easier to do. And
Yeah.
then with these two pieces of information we can look at test the hypothesis that essentially Irwin's law can be made to be time dependent with an additional closure relation.
Okay.
That's cool. Awesome. Well, I don't want to take up more of your time. It's Friday afternoon, and perhaps one of these days we can get together and explore potential collaborations.
That'd be great. Yeah. That'd be great, Rami.
All right. Thanks again, Will.
Thank you. Thank you again. I'll see you around.
Yeah, I sure appreciate it. Have a good
All
one.
right. You too.